better now? Do you want to try? Can you hear
Hi.
me still? Oh, no.
Hi. Yeah, I think it's much better now. Cannot hear the loop anymore. Okay.
Uh,
Okay. I'm ready.
okay, go for it.
Okay. Hello everyone. Uh, Thank you very much for the opportunity for me to present my work here. Today I'm gonna talk about perspectives on thermodynamics of non-stationary horizons from two approaches. I'm Zihan Yan from Trinity College, Cambridge. And today my talk is based on these works with Aaron Wall and Manus Visser, and some upcoming work with Stefan Hollands, Manus Visser, Bob Wald, and Victor Zhang. And so, um, before I start the main question of today's talk, let's do a brief recap of black hole thermodynamics in GR. So we know how ordinary thermodynamic system would behave. So we have the zeroth law. We can define the temperature that is the same for two systems that's in thermal equilibrium. And also we can study how the energy conservation would work for any thermodynamic system. The increase in internal energy is equal to the heat flux and plus the work done by the system. And also, we have for a closed system, the thermodynamic entropy will never decrease. On the other side, we have similar laws in black hole mechanics. So for a stationary black hole, we could study a quantity called surface gravity. Namely, you have some particle near the surface, near the event horizon, and you're holding it at infinity. And basically, this is proportional to the acceleration you exert on the particle. And then this is constant for a stationary black hole. And also, you can compare nearby black hole solutions by varying its mass and angular momentum. And you can see the variation of the mass and angular momentum is is related to the changing event horizon area by this law. And famously, Hawking proved the area theorem, saying that the event horizon of the black hole will never decrease. And so Hawking calculated the temperature when you put quantum fields on the black hole background, and then the black hole became a radiating object, radiating at a temperature proportional to its surface gravity. So by this identification, we can match the temperature with the surface gravity, and also we can match the entropy with the event horizon area. So then you can identify the laws of black hole mechanics are truly the laws of black hole thermodynamics. And this is the story in GR. But in our talk, I will ask another question. What is the entropy of a dynamical horizon in any theory of gravity? So this is motivated by the goal of understanding quantum gravity. So the question itself is too hard because we have less and less understanding from the infrared to the ultraviolet. So in the IR, we have general relativity, which is like really well known and well studied in the past century. But towards UV, my approach is actually a bottom-up direction by deforming the general relativity in irrelevant directions to get diffeomorphism-invariant effective field theories with higher curvature couplings. So these higher curvature corrections actually captures the quantum or stringy effect in long distance. And so we want a theory-independent clues uh, from IR towards UV. So we want to understand the universal feature of semi-classical gravity as a diffeomorphism invariant theory, not just GR, but the whole vicinity of GR in theory space. And so what we do is we use general higher curvature or non-minimal couplings to probe these features. So we start with a very general class of Lagrangian that is constructed out of the metric, the Riemann tensor, some matter field that can be non-minimally coupled, and their higher derivatives. And so essentially, we want a general framework that is applicable to any IR effective field theories of quantum gravity. For example, we could consider the low energy effective field theory of string theory with alpha prime corrections and various matter fields. But we asked such a question to a great generality. So it remains open, like what can still be asked and said, because the setup is too general and the too few assumptions are provided. So we want to understand what features would persist beyond general relativity and what kind of IR constraint, some universal constraint, are given for the UV quantum gravity, so that for any UV complete model, we can flow it to IR and test it. So one set of the constraint that we can consider is the behavior of light rays. So we can measure we can measure the space-time using light rays. And in general theories of semi-classical gravity, we want to understand the behavior of light rays under some positive energy flux. So in GR, we know that the positive energy density would curve the space-time so that the light rays would focus. But is this still true in general theories of gravity, and to what extent? And also, is gravity still attractive in a universal sense? And so, also, we want to ask the question whether Riemannian geometry is still compatible, because we now know that for a general theory, its equation motion tensor is no longer the Einstein tensor. It does not necessarily have a special geometrical meaning as the Einstein tensor. So in order to see a universal picture of light ray focusing or attractive gravity, what kind of geometry should we upgrade to see this beyond general relativity? And also, we want to see how universal the light ray focusing is and what kind of barrier would appear, and would this give any no-go constraint to the space of theories? I will talk about how the consideration of light ray focusing can give you some physical consistency conditions for higher spin theories. And then, if this idea is universal, can we extend the notions of trapped surfaces and apparent horizons to any theory of gravity? And also, can we say something about singularity theorems in general?
Can
So,
I ask a question? Can
yeah.
you go back? So I didn't quite understand the third bullet point. Maybe you could expand that Riemannian geometry in general is not compatible with general theories of gravity. What do you mean by that?
Yeah, because if you're just well, I will talk about this later. It's because if you now consider you just turn on some positive energy source, and it will not curve the space-time in a usual way that you expected as in GR. So, so for example, you can see light rays defocus because it can see some effective negative energy caused by these higher curvature corrections. But then, if you just change your perspective, so you upgrade your Riemannian geometry to some new kind of geometry, although the full picture is not complete, as I will show, and then you can see the light rays would focus in a universal way. So this is basically, and also I think in general, higher curvature theories, the consideration of causality is really complicated if you still work with the Riemannian geometry. So I mean, my speculation is that you should upgrade it to certain kind of Finsler geometry. Yeah, but that's some future work. Is that
Okay, maybe I'll wait and ask again if it's not clear later also.
okay? Sure. So yeah, or maybe to add to that, I'm just questioning whether Riemannian geometry would still be a good kinematic framework to describe gravity in the general sense. Okay. And also, we can consider another set of IR constraints is by horizon thermodynamics. So we know that there is always some entropy associated to a horizon, and then it, to some extent, enables us to count or bound the number of microstates of the UV physics using some IR information. And then, so the key question is, can we obtain a general entropy formula for any theory? So it's a functional of the Lagrangian and also a functional of the some arbitrary cross-section of the horizon. And then we know that in GR we have the Bekenstein-Hawking entropy formula, which is proportional to the area of the event horizon of the black hole or any causal horizon. And then uh, in equilibrium, we also have the Wald entropy. But can we extend beyond these, for example, to some non-equilibrium cases? And from these, what kind of IR constraints can we draw? So maybe a potential answer that I'm sketching is if we know such a formula in the vicinity of GR, so well, in within the validity of all these effective field theories, and then we can actually study the RG flow within this EFT region. And we can study the flow function of this entropy functional when you just change the energy or length scale. And you can see how that would flow with the coupling constants and the corresponding metric where you study with the horizon that you're studying and also some matter field. So the upshot is if we believe this entropy should encode exactly the underlying microstates, and then it will the number should be unchanged under that flow. So you can just write down such flow equation and will depend on for example, some beta functions and how your horizon solution would change when you vary the length scale. And then probably it will, you can set this flow function to zero and that will give you certain constraints. So that's the speculation. But before we do that, we need to understand the part that such an entropy functional for general theories and general surfaces. And so so this leads to another ultimate goal. Basically, we'll want an entropy formula for general codimension to spatial surface, because if we understand these, we will get better we'll get a better information on how the quantum information would flow locally through any such codimension to surface. And then we can just understand certain constraints and we can test all these UV complete quantum gravity and when they flow to IR. And so what we have is the entropy in general relativity, so the Bekenstein-Hawking entropy in equilibrium, and we can actually go out of equilibrium, and then we can also push it off the horizon. But also, we can do it a little bit, deform it a little bit to the UV by considering all these higher curvature corrections so that you have some general diffeomorphism-invariant theories. And then there, in equilibrium on some causal horizon, you have the Wald entropy. And the goal is to first understand what is the situation when you go out of equilibrium. And so we will go beyond equilibrium to first order of dynamical perturbations. And then we can already see some universal features would emerge at this order. But like in general, we want to push it to anywhere. So some arbitrary codimension to surface. But as a first step, we need to understand the near equilibrium entropy for some causal horizon in general theories of gravity. And
Can
then,
I ask, sorry for
yeah,
interrupting. Can I ask, I didn't quite get, for a general codimension two spatial surface, what is the entropy supposed to mean or count?
um, so basically, in some upgraded picture, if you just believe gravity is some well can be described holographically in an asymptotics independent way, then for example, in the case of Cauchy slice holography, and then you can always associate some codimension to some entropy to this codimension two surface that actually tells you something about the bond dimensions in your like low well in the quantum field theory on the Cauchy slides. So it's like some tells you like how much information can flow through this cut.
Okay.
Okay. So as a first step, we need to study near equilibrium entropy uh, because that's the first and non-trivial order when you can see coarse graining and second laws, and that can give you some new constraints. And we work with two approaches, light ray focusing and symmetry. And these give two different but interrelated entropy formulae, known as the wall entropy and the Hollands-Wald-Zhang dynamical entropy. And this goes beyond the general relativity and goes beyond the equilibrium to first order. And then we can already see these two entropies actually tells you how to relate surfaces on the event horizon and off the event horizon. Namely, in this case, it's the apparent horizon. So because the question that we ask for general entropy formulae arbitrary theories is too hard, we need some scaffolding. So we start with some background in thermal equilibrium, and then we perturb it linearly. And so we just start with this regular bifurcate killing horizon, and that actually covers the case of Rindler horizons, black hole horizons, and de Sitter horizons. And then we ask the horizons to settle down to equilibrium at a later time. And so, as a technical assumption, we also first demand the field contents to be smooth, but later we'll relax this for gauge fields. And so, I first talk about how can you get an entropy from the consideration of the behavior of light rays on the horizon. And then I will talk about how do you get such an entropy from the consideration of Noether's theorem. So the first question we ask is that do light rays still focus under positive energy flux in any theory of gravity? So we start with GR and then generalize to arbitrary theories and see how these can give us constraints for higher spin fields. So if we just take a bunch of null geodesics, some bunch of light rays on a null hypersurface, and then we can write down the Raychaudhuri equation, basically describing how its shape would evolve along the null direction. And then if you look at this picture, so here, this curly A is the area element spanned by some nearby light rays. And this basically tells you how close by these like neighboring light rays are. And theta is the rate of change of this area element, giving you the geometrical expansion. And also this sigma is shear, telling you how the shape, while preserving the area, would change. And so the Raychaudhuri equation is a purely kinematic equation describing the change of the shape of such bunch of light rays. And then if we just input the dynamics here by plugging the Einstein equation, we know the curvature is sourced by some stress energy tensor. So now we take the thought experiment by throwing in some non-energy flux with positive psi, and then we immediately prove a geometrical focusing theorem. So if you look at the right-hand side of the Raychaudhuri equation, so the first two term is minus of some perfect square. And also by the non-energy condition, you can see this curvature term is also non-positive. So this will tell you the geometrical expansion will never increase along the null direction. And so light rays would always focus under the influence of positive energy. And so that's a manifestation of the fact that gravity is attractive. So as you can see, these light rays would just try to go near to each other. And once they start to converge, they will converge to some conjugate point in finite time. And this theorem is basically well, it underlies the famous Hawking's area theorem, telling you that the black hole event horizon is always non-decreasing. And then also this tells us this underlies the famous Penrose singularity theorem. So we know that to describe focusing, we need a measure of proximity between light rays. And in general relativity, this is actually given by the area density. But we also know if we just put this picture on some causal horizon, we know that we can change the area of the causal horizon into the entropy of the causal horizon, because these two are related by the Bekenstein-Hawking formula. So we can actually change our perspective so that now the entropy density can be thought of as a measure of proximity for a fixed bunch of light rays on the horizon. So if you have, so in some sense, if you have more entropy squeezed between light rays, and then you can say they're further apart, and vice versa. And this profound shift in the perspective will actually be very important when we go beyond general relativity. So currently in GR, it's just a trivial identification by the Bekenstein-Hawking formula, but it will tell us something more universal. So when we go beyond general relativity, we would have these higher order correction terms in the equation motion. And then if you plug this back into the geometrical Ricciardo equation, you will immediately see some term here that would just have some indefinite sign, because the sign of this correction term will determine on the sign of the coupling constant that you have, and also it will be determined on which solution you're evaluating that in. And so this basically tells you light rays would no longer focus geometrically, even if you source the dynamics using some positive energy flux. So seeing by this geometrical expansion, there will always be some negative effective null energy caused by these higher order terms. But this is expected because this calls back to the statement that I said the dynamics is not compatible with the Riemannian geometry here, because the Einstein equation, the equation motion is no longer the Einstein equation, and then it is the gravitational part is no longer the Einstein tensor, which does not always have a special geometrical meaning, because the Einstein tensor is the unique, well, up to some cosmological constant terms, is always the unique divergence-free term at second order of derivatives that can be constructed out of the Riemann or Ricci tensors. And so if you have higher order terms, and then I don't know whether there are any more special meaning. And so,
Sorry, just a question. Can't you treat your higher order terms as if they're just the form of stress energy with strange, not satisfying any nice energy condition necessarily?
in some sense, yes. But then, well, that's one way of thinking. Or maybe you could also argue these things can obey some other kind of exotic energy condition and serve as constraints on these higher order couplings. But I actually take another perspective, but basically by absorbing these higher order terms into the expansion. So then I will have a more universal picture of light ray focusing.
Okay.
Yeah. So, well, this way of doing things is based on the belief that gravity should still be attractive in some universal sense. And so let's see how it goes and whether it will be successful. So in this approach, we want to generalize expansion for any theory such that it obeys the fact that it will never increase under positive energy flux. So we just want the null energy flux to directly source such a change in the generalized expansion. So, and also if this thing exists, we would need to require it to itself to be some rate of change of some density. And this would be the entropy density, but I haven't justified it. And so, as I said, it is in general a very hard question, but it's doable for linearly perturbed Killing horizons. So, in a decade of work, including my work with Aaron Wall, uh, if you consider the class of diffeomorphism-invariant theories that constructed out of the metric, the Riemann tensor, some scalar fields and vector fields, which can be either gauge field or Proca field, and their covariant derivatives. And then if you just write down the off-shell structure of the null-null equation motion tensor, and then it will admit a structure that looks like a Ricciardo equation, so that I call it a generalized linear Ricciardo equation. And so from here, you can see the null-null component of this gravitational equation motion on the horizon can be written as a total null derivative of some scalar density. And then there will be some higher order corrections. So this epsilon is the parameter in the dynamical perturbation, so that how far away you are from equilibrium. But to first order, we have this universal structure. And so if we further unpack what's the content for this generalized expansion, we can see it is actually a rate of change of some density and a total spatial divergence of some current. I call these entropy density and entropy current, but I haven't justified why these are related to the entropy. But before we actually go to the justification, we can see some nice universal feature already emerges. So if we redo the thought experiment by sending in some external matter field that gives you a positive null energy flux, and then if you plug this stress tensor into the equation motion, and that will source this generalized expansion and make it its rate of change to be non-positive. So the generalized expansion would never increase. This would be universal for all theories at first order already. And this gives us an alternative geometrical picture. If we reshape the light rays in terms of this S and J density current. So on the left-hand side, you can see that you have the Riemannian geometry picture, and you just measure how close by light rays are using the area element spanned by them. But because of these higher curvature terms, it can focus or defocus and in general do very weird things. And so this is a very exaggerated picture because actually what I said is only true universally to the first order away from equilibrium. But on the right-hand side, if you just try to replot the area spanned, some generalized area spanned by these light rays using this S and J, and then you can recover the nice focusing picture as we see before in general relativity. So this is like one of the universal feature for any theory of gravity that we can see by the consideration of light ray focusing. So we have always, we repeated calling these entropy, density, and current. So how do we know they're associated with the thermodynamics of the horizon? So if we consider a horizon with compact cross-section, and we integrate the density S, and we obtain a scalar quantity known as the Wald entropy. It is defined by Aaron Wald back in 2015 for pure gravities. And is this thing well defined? Yes, because it gives the correct horizon thermodynamic laws. So if we slightly modify the focusing equation that we started with, so this thing, and then we just upgraded one of that to your background Killing vector, And then you obtain this equation, and then you can integrate it on the horizon from the old bifurcation surface all the way to future infinity. And then you can see the change in this quantity is related to the total change in the total Killing energy flux, which is in turn related to the change of the mass and angular momentum, and also maybe if you have an electromagnetic charge for your causal horizon. And so this gives us the physical process version of first law. Also, if you just integrate the focusing equation on any codimension 2 cut, and then you would obtain an integrated version of the focusing theorem that the second derivative of the wall entropy will never increase. Together with the settle down condition, you would obtain the second law. So if you look at this picture, the distance between these nearby light rays are measured in terms of this wall entropy density. And by our settle down condition, these light rays want to be parallel to each other at future infinity. And also, we ask these geodesics to be complete so that it will just go on forever. So because of this future teleological boundary condition, that would tell you that the horizon wants to expand in the sense that this entropy would increase. So to give you an impression, we have tried to calculate the entropy formula for such a general class of theory. And so the first term you see here is the Wald entropy. And then all these are the dynamical corrections. And so these are calculated using some Gaussian null coordinates for convenience, but it's actually proven to be invariant under the choice. But if you try to add another derivative on any of these dynamical quantities, it's actually become really complicated. And I tried to calculate by hand, and it seems to take hundreds of pages. So currently, we're trying to using some machine learning technique, namely the symbolic regression, to determine these differential operators that acts on the Lagrangian to get the general formula. And this is important for some reason that I will mention briefly. But before we do that, let's review the property of the wall entropy. So it follows from the focusing, and also it is an integral of local geometrical quantities. And also, it obeys the laws of thermodynamics, and it's unique in the sense that it does not suffer from any of the ambiguities in either the hydrodynamic sense or in the covariant phase space sense, because it comes from the equation motion, which is entirely unique, well, unambiguous. And it has the correct correspondence because it goes back to A over 4G in GR and goes back to Wald entropy for stationary horizons. And as I said, it's covariant under different choices of coordinate system. But most importantly, it shares the same formula in F-Riemann theory with the holographic entanglement entropy calculated by Xidong. So this is like the generalization of the HRT formula when your bulk contains higher derivative corrections. And then if you look at this formula, this is the Dong entropy formula for F-Riemann theory. It looks exactly like the F-Riemann case if you just consider the first two terms for the wall entropy. But the full equivalence of both sides is still a mystery because they come from a very different consideration and very different calculation, one Lorentzian and one Euclidean. So I'm just wondering whether there would be some universal entropy formula governing all these, and it somehow selects some preferred expression for a general class of Lagrangian.
So the asymptotics of space-time don't matter for the formula at the end?
So for the wall entropy formula, the asymptotics does not matter as long as you have this bifurcate Killing horizon background to start with. And so you could consider asymptotic flat or ADS. And also, if you just look at pure DS in higher curvature gravity, and this will be the DS entropy. And so it will just work for any asymptotics.
Uh-huh.
Yeah. But I think the Dong entropy relies more on ADS-CFT. Yeah. And so as I said, so I just presented the generalized focusing theorem for pure gravity plus scalar or vector fields. But what about higher spin fields? So at first order of the perturbation, the consideration of focusing is actually too coarse to constrain anything, for example, the causality or well-postedness of your theory. Because I've received many questions and saying whether this will tell you, okay, some theory would they contain ghosts or some other things. But unfortunately, this is like a universal kinematic framework that would apply to all these like lower spin fields, except higher spin fields. And at this level, constraints already would appear. So if we reconsider this Raychaudhuri equation, now when we turn on some higher spin couplings in the Lagrangian, we can see there is a barrier, some indefinite term that cannot be absorbed into the definition of this generalized expansion. So it will, in general, break the structure of the Raychaudhuri equation and break the notion of focusing or entropy or thermodynamics, anything. So, but this is expected because if I just arbitrarily write down some higher spin theory, it's going to be wrong to some extent because actually you need very intricate symmetry or some very nice way of tuning the couplings so that you do not have any inconsistencies. And so I actually propose that we use this light ray focusing as a physical constraint to test the consistencies of any higher spin coupling that you write down. And so I actually proposed this higher spin focusing condition by demanding that this barrier term would be zero for any sensible theory. So
Is that true? Oh, yeah, I guess you're going to say it. Sorry, go ahead. So go ahead.
oh yeah. So I'm just telling you what's the content of these barrier terms. So, for example, for spin 2, you have these null polarizations, and spin 3, you have all these. So essentially, these are just polarizations when you have two or more outgoing null indices than the ingoing null indices. So in the language of well, how they transform under a rigid boost, and then these quantities would have the boost weight 2 or higher. And so one way to meet such focusing condition is such that these higher spin theories has enough gauge symmetry to ensure all these higher boost weight polarizations are zero near the horizon. And so I call this the gauge type focusing condition because this reminds us something about the temporal or longitudinal polarizations of the one-form gauge field. For example, we can always choose a gauge that the outgoing null polarization of some one-form field vanishes on the horizon. And so, but we also need to emphasize that focusing itself is gauge dependent for higher spin fields because to trace back, the horizon themselves are also gauge dependent because as these papers have shown, you can start with some solution that has a causal horizon and then sorry some event horizon, and then you just do some non-trivial higher spin gauge transformation and you result in some other theory with the other causal structure where you do not have a horizon, but that is fine. So the upshot is like for any higher spin theory, for any solution where there is a causal horizon in a particular horizon gauge, so if the higher spin focusing condition cannot be satisfied by the dynamical perturbations in this gauge, and then I would call this theory would be inconsistent. So it's more like a no-go theorem. So anything that violates, so any theory, somebody tell you they have a higher spin theory, and then they tell you they have a horizon, and you should ask them the question whether these polarizations are zero in their gauge. If not, you will have inconsistencies and you cannot say anything about focusing or or you cannot define the entropy of that horizon. But
This is for higher spin massless only, right?
uh, so far this gauge type condition is aimed for this massless higher spin fields. But for massive higher spin fields, I think it will work in some way. Like there's always some consistent Stuckelberg trick that you can do on these fields, so that they can be unpacked into some massless higher spin fields, and also a whole tower like reduced to some derivatives of some lower spin fields. So you can trace all the way back to the case of vectors and scalars and use the previous result to see, okay, these components are actually not problematic.
Interesting. Okay.
Right. So
can we also go back 1 second to if I looked at some theory that had like a d phi to the fourth like interaction, or some nice high derivative interaction with scalars, is the sign of that interaction is bounded by scattering constraints.
right.
From a long time ago. Are those constraints manifest here? Does something go wrong in your focusing analysis?
Are you thinking about higher derivative or higher spin?
Higher derivative. Like even for a scalar, just like d phi to the fourth.
Okay. So as I said, for scalar fields, I think the consideration at least at the first order away from equilibrium, the consideration of light focusing is too coarse to see any like better constraints to tell you something about the ghosts. So, but I presume you need to go to like higher order away from equilibrium, or higher order in the like deformation of the shape of the parallel light rays to see those constraints, I think.
Okay. Sorry, one other question about the highest spin here.
The higher spin, so basically, as I said, for scalar and vector fields, these the framework of light refocusing is coarse, but already at this order, at first order perturbation away from equilibrium, and it can sense some pathologies in higher spin fields. So basically, yeah, higher spin fields are easier to be diagnosed within this framework.
I mean, does the analysis break down if you had a tower of higher spin fields versus a couple, a finite number?
I think, well, I don't think it would,
It would
well,
break.
I could only, well, I mean, maybe the gauge type can break down in some sense, but you can still calculate, maybe you can sum everything here, because then if you have a whole tower of higher spin fields, and that should be actually the real case, and then you can resum everything and to determine whether this barrier term or indefinite term would vanish. But I haven't really calculated that. Right. So there are like different ways of satisfying these higher curvature, sorry, higher spin focusing condition. So one way is somehow you have all these nice gauge symmetries, and that's easier to see. But I suppose it's more about the structures if you have a whole tower, and maybe there are some consistency conditions that, yeah, to be tested here. But you need to write down the equation motions and see what's there. Yeah.
So this is all based on the physics of saying I want focusing because that's
Yes.
somehow analogous to having good thermodynamics.
Yes.
In the story. Okay. Okay.
So it's like I demand focusing for the sake that I have some entropy that is local in the sense that only depend on one time slice. So if somehow, I mean, the equivalent statement is that if I break this higher spin focusing condition, I actually would have some entropy that is non-local because it depends on the information and future infinity. So which is I don't want. Yeah. So yeah, I just tested some YESCO example. So some 3D higher spin gravity in the Chern-Simons framework, and then there is a solution with a spin 3 field, and it claims okay they have a black hole gauge. So I just translated this into the null coordinates, and I immediately see their gauge satisfies the condition that I asked. So there you could also turn on some dynamical perturbations, because ideally these will never break the gauge symmetry of your theory. So you can see this in this specific example, the Harbin focusing condition satisfies. So we can talk about the focusing theorem and entropy and the thermodynamics, etc. So now I'm going to another perspective, namely the Noether's theorem, because as I said, we have a background equilibrium, have a background killing symmetry. So there is a conserved quantity associated to it that will give us the entropy. And so I will first talk about the Hollands-Wald-Zhang dynamical entropy, and also say how we generalize that to study the case of black objects with p-form charges and non-compact horizons. So this is motivated by some string-inspired models like charged black branes or black strings. And also, in the end, I'll tell you like how this unify with the wall entropy through the notion of generalized apparent horizon. So we know Bob's famous paper, black hole entropy is Noether charge. So indeed, if we have a situation in perfect equilibrium, we can see that the entropy of this horizon is given by the Noether charge of the background killing symmetry, because it relates correctly to the ADM mass and angular momentum at spatial infinity. And so, and we know in the perfect equilibrium, the second law is just trivial because it's a constant. But we also know that because our quantity, the Noether charge is defined on this covariant phase space language, and then there are some ambiguities in how you define these differential forms, known as the Jacobson-Kahn-Myers and also Wald ambiguities. So if you start with the Lagrangian and you do a variation, you have the equation motion, which is unambiguous, but then you have some boundary term. So this definition of the boundary term is only in terms of d theta, and this theta is nothing related to the generalized expansion that I talked in the earlier section. And so this is only defined up to an exact term. And so also, if we look at how the Noether charge is defined, it actually carries forward this y ambiguity, and also itself has some exact term because it only defined by dq. So if we just consider this particular type of ambiguity in the Noether charge, and it has a structure that is linear in the Lie derivative of your dynamical field. And so all these ambiguities would vanish in perfect equilibrium. So the Wald entropy is intact. But whenever we turn on some dynamical perturbations, and then the Noether charge is ambiguous, and then you can shift the value of the Wald entropy arbitrarily beyond the stationarity. And so there's no second law. But so we need to cure this if we want to have something that's not ambiguous. One way to do this is use the wall entropy from the light ray focusing that I described, because that is from the equation motion. And then there's another approach by consider the truly JKM ambiguity invariant surface charge. I also call this improved Noether charge. So alongside this variation of the Noether charge, you add back the contribution from the boundary term that you obtain by varying the Lagrangian, so that the whole thing would transform accordingly. So the total ambiguity is the exact term, and when you integrate that on some compact surface, it will be zero. And so the variation of a target dynamical entropy is defined accordingly. So this is given by Hollands-Wald-Zhang last year. So you define the variation using the variation of the Noether charge, but which is not ambiguous. However, as you can see, the validity of this definition relies on the path independence of this variation in the phase space, because we know here you have a perfect delta exact notation. It's a total variation. But here the boundary term, it only depends linearly on the variation of the field contents. But then you need to ensure the delta can be pulled out, at least well in the back well in a background with the killing symmetry. And so Hollands-Wald-Zhang proved for pure gravity that there exists some codimension one form on the horizon, such that this Lagrangian, this boundary term from the Lagrangian can be written as a total variation of the speed term. So you can just change this delta bar to a real delta because now this variation is exact and it's independent of path. So this is crucial for the dynamical entropy that you want to define to be a state function. So in general, if you improve the Noether charge, you obtain the dynamical entropy. So relatedly, in my work with Magnus Visser, we generalized this from pure gravity to include arbitrary non-minimal bosonic matter fields, well, including higher spin fields. But then I'll tell you like why you can define it in general here, but not for the wall entropy in the end.
Can we go back one second? So
Yeah.
on the previous slide, the wall entropy approach. So one slide before this. So the wall entropy approach. Oh, sorry. Maybe it was the. Oh yeah, right there. Using S-wall. You said that follows just from the equation of motion.
The wall entropy, yes, because if you go all the way back, this entropy density is extracted from the equation motion, the nominal component of equation motion on the horizon, and it's like an off-shell extraction because you can just write down its structure and it's there.
Is there if I formulated this from a Lagrangian perspective, that shouldn't that have been equivalent to some specific choice of
Yeah.
term here?
Of course, it's actually more subtle. It does not have like a nice way of writing it in terms of this as some improved Noether charge of some symmetry. But what I can tell you is that its first derivative, so it's related to the integration of the generalized expansion, is actually equal to the Hamiltonian of the translation, the affine translation on the horizon. So if there you have a positive translation energy, and then you have a second law. So in that sense, so it's like very indirect how it relates to the Lagrangian or coherent phase space formalism. And then, yeah.
So it's not local, so not necessarily any local boundary term that you could write down that would reproduce that.
Yeah, it's still some local charge, but it's very indirect. We can chat about that maybe later.
Yeah.
Yeah. Okay. So what's the nice property of this improved Noether charge? And so it actually is conserved according to the fundamental identity. So it's some sort of gravitational Gauss law. If you try to evaluate it at two codimension two cross sections, so I put one on some arbitrary cross section of the event horizon, and put another one at spatial infinity, I actually obtain the comparison version of first law. So here the delta is different than the first law before because now we're comparing the background equilibrium solution with a dynamically perturbed solution where you do not have time translation symmetry. So in that sense, it's a generalization beyond the stationarity. And also, we can consider the source, the gravitational Gauss law, by some external stress energy tensor, aka you're throwing some stuff into the horizon. And then you can compare some two arbitrary cross sections of your event horizon, and then see how that relates to the total killing energy flow into the segment between these. And then you actually have a more local or arbitrary version of the physical process first law, because now you can just compare arbitrary cross sections, while the wall entropy only satisfies such a physical process first law when you put one on the bifurcation surface, one at future infinity. And so you could also take the limit that these two cross sections coincide and then you obtain the linearized the second law. Basically, the entropy will never decrease when you have some positive energy flowing in. And so you can also compare with the definition of the wall entropy. So this is another way of writing like how you define the wall entropy, and then you obtain a nice and simple relation between these two. So curiously, in general relativity, the dynamical entropy is not the A over 4G, but it has some correction term here. So as a case study, I applied all these to charged black objects in a recent paper. So here we actually relaxed two more assumptions. First, before we demanded regularity of my matter field on the horizon, but now I can relax that for p-form gauge field. And also, I could relax the compactness assumption of horizon cuts so that I can consider the geometries like branes or strings, etc. And so this is actually all applicable to string-inspired models, for example, some charged black branes or black strings. So we start with some non-minimal coupled p-form gauge field in a gauge invariant manner, where this F is the field strength, and I could have some other matter fields. And then maybe I could also add some other terms so that these matter fields are coupled to this F in some gauge covariant derivative. But like for simplicity, I'll omit these discussion in the talk. But then the relaxation of A actually allows for non-zero electromagnetic potential, because the potential is C dot A, where this C is the background killing vector, but it vanishes at the bifurcation surface in the background. And so if you want to have a non-zero phi, this means A has to be divergent at the bifurcation surface. So that's why we wanted to remove this assumption. And so this actually gives us more like technical difficulties in like treating these divergent gauge field terms on the horizon. So what we did was split this improved Noether charge into a gauge invariant part and a gauge dependent part. And so the gauge dependent part contains an electric term and a magnetic term. And here we just focus on the electric term. Basically, this epsilon is like the generalized electric flux density that goes back to star F for free Maxwell action. And so, moreover, we can just evaluate all these at different places. So we noticed that the gauge invariant part at spatial infinity will also, as before, give you the ADM mass and angular momentum. And so if you just consider the sourceless pure electric case, and you use the gravitational Gauss law, you can just match the improved Noether charge at the event horizon, some cross section there, and also that at the spatial infinity. And so you can just like put each of these terms. So on the right hand side, basically this term it will be the variation of the mass and angular momentum. And these gauge-dependent terms give you some higher form generalization of the phi delta Q terms. So the electric potential and charge terms. So what remains is the integral of the gauge invariant improved Noether charge at the event horizon. So by this, you can immediately identify that this would be the dynamical entropy of your charged horizon. And it is gauge invariant as it should be. So we also analyzed what's the details of such electric potential charge pairs. And then we actually proved the constant potential law, the zeroth law, for higher form fields. And so that you would have some higher form analog of constant potential at the event horizon and also at spatial infinity. And you can do all these algebraic topology trick so that in the end, it can be evaluated to all these charges on some lower dimensional non-trivial cycles with the appropriate dimensions, because we know that when you go higher in the degrees of forms and you actually go to lower codimension surfaces, sorry, higher codimension surfaces, lower dimensional surfaces, where these electric charges would localize. So, for example, if you consider a black ring that's charged under 2 form, and then your charge would pick out this sphere. So it's like a circle times the sphere, and it will localize on the sphere. But if you consider black fold, where you have a torus in the sphere, and then you have two ways of choosing like where to localize. So you have essentially two different species charges. One is the red circle with the sphere, and one lives on the blue circle with the sphere. We also consider the non-compact horizons because we want to study what's the thermodynamics for black strings and black rings when they are charged. And so we actually saw that the electric flux density and potential pair terms can give you more species depending on how many legs they have in the non-compact directions. So, because in general, for a non-compact geometry, it's hard to talk about these Hodge decompositions or Poincare duality. But then we just used some fiber integration technique to actually project them back to the compact subspace so that you have a whole tower of different species of possible electric charges, depending on like how many legs you have in these compact dimensions, compact directions. And so we just saw many species of charges are kinematically loud, and I want to ask the natural question, so do we see them in string theory? So that's probably a next set of projects to explore. And so to wrap up, we can write down the first law for charged black objects. So then we can recover all these precise electromagnetic charge potential terms, depending on the topology of the horizon. And so in the end, I want to tell you how the wall entropy and dynamical entropy would unify. And so,
Zihan, are you nearing a conclusion?
of course, yes. It's just two, three slides, quick slides to go. Yeah.
Try to wrap up in the next couple minutes.
Okay. Yeah. Thank you very much. And so previously, we have seen the relationship between the dynamical entropy and the wall entropy. It's nice and simple, but we haven't talked about the physical picture of this. So if you just evaluate this in GR, you will see this means the dynamical entropy all associated to the event horizon is equal to the area over 4G of the apparent horizon that's related to this event horizon. Because in the dynamical situation, the local boundary of your trapped region is essentially different from the global event horizon. It lies slightly inside the event horizon. So actually, this dynamic entropy captures the area of the apparent horizon that lives inside. And so in a work in progress, we're trying to define a generalized apparent horizon where we want to write down a covariant condition where this generalized expansion would vanish. And so there you would have the similar relation that the dynamical entropy associated to the event horizon is equal to the wall entropy associated to the generalized apparent horizon. And so essentially this condition will, this marginal trapped condition will give us the stability PDE of this generalized marginal outermost trapped surface. And so to give you a very quick taste of how these two entropies would behave, so I'm doing something like really wild here. I'm sending in some delta function poles, and this in general should be smeared, and we're actually going way out of like first order perturbation. But as a test of principle, we can see that if we just send in such a delta function, by teleological boundary condition, the wall entropy starts to grow even before the pulse falls in, and it becomes constant afterwards. But then the dynamical entropy would just jump during this infalling of this delta function. So the wall entropy corresponds more to global description of causal horizons. So you have more global information and it's less coarse-grained. But then this dynamical entropy gives you the local behavior and it gives you less information, but probably more coarse-grained. And so here you can see this blue line labels the position of this generalized apparent horizon. So it lies inside and then it suddenly coincides with the event horizon. And so to conclude, I want to tell everybody how this research of non-stationary horizon thermodynamics embeds into a bigger program. So the goal is to pursue a general understanding of gravitational entropy and also try to use that to decode underlying microscopic degrees of freedom. And so in this diagram, actually, I have like many different projects associated to each edge. So starting the turf of the IR classical or semi-classical gravity, you could use based on this framework to try to obtain more constraints. For example, you could refine the entropic geometry that I described, and also to really study the flow functions of the EFT entropies that I described in the motivation slides. And also, as I said, I mean, if you have higher order corrections, and the causality is actually quite problematic when you describe it in the Riemannian geometry. So should we really use the true fastest propagation surface determined by some Finsler cone? But so you need some upgraded notion of a null hypersurface. And also there are three different directions that you can go. You can go also all the way away from GR and classical or semi-classicality by considering some quantum fields on this curved background and consider general quantum focusing theorems, quantum entropy bounds. And also you can go all the way from equilibrium and to study the real hydrodynamics of null hypersurfaces. And also I want to go away from causal horizons to really see what's the entropy for general codimension 2 surfaces. And also, you could relate that to conventional ADS-CFT, for example, matching wall entropy with dome entropy because they share the same formula, which is still a mystery. And also, you could study what's the boundary description of the dynamical entropy that I just talked about. And my speculation is that it's related to the simple entropy on the boundary, corresponding to a specific coarse graining scheme. But we just need to determine which set of boundary operators these coarse graining procedure would preserve. And also, like to really study the entropy of some general codimension 2 surface on some general Cauchy slice, I want to integrate this into the framework of Cauchy slice holography, which is an asymptotics independent way of doing holography. And recently, there's a paper by Aaron and collaborators on holographic covariant entropy bound. And it actually takes the same expression as the dynamical entropy. And I want to understand this further. And in general, can we compute the entropy by considering the entanglement entropy of these T-square or TG bar deformed Cauchy slice field theories? And also, I want to see whether we can say more about the path towards UV completion. For example, I just want to understand better the process of black hole information paradox and like whether there's some entropy bound will tell you where and how post-selection would happen. And also this Cauchy slice holography exhibits some Z2 cross Z2 spectral symmetry associated to the density of states. And then I just want to understand how that is related to the gravitational entropy. And so that's the end of my talk. And thank you very much. Sorry for running late.
Okay, questions?
I had a naive question. So just to try to understand your motivation a little better. So you're using this focusing as kind of a guiding principle.
Yes.
But I guess it would be violated by any quantum field theory, which doesn't satisfy the null energy condition. So is there a version of your story that allows for quantum field theory?
Of course. So if you just try to add the expectation value of your stress tensor here, and then actually you could use the quantum null energy condition so that you can repackage the derivative of this relative entropy, or say the entanglement entropy, and integrate that with the wall entropy. So you actually obtain a generalized entropy for arbitrary theories. So it's not A over 4G plus SQFT, but it's more like S wall plus this entanglement entropy. And there you have a generalized second law. And it's more like a generalized quantum focusing. But I mean, actually, in the in the future work that I intend to investigate is, can we actually first prove some principle like a quantum focusing theorem, and then just derive everything else from that, like the generalized second law and the quantum non-energy condition, quantum Boussel bound, etc. Is that clear?
Can you do that in ADS-CFT already? Is it, can you formulate it?
You mean quantum focusing, or?
Focusing as some principle about a correlation function in.
I think it's I'm not sure like how that is I'm not entirely sure how that is like manifest at the boundary side, but probably somehow, yeah, you can associate it with some core screening procedure on the boundary, so telling you like certain operators are preserved, and then you're maximizing among a bunch of core screened density matrices. But I'm not entirely sure like how that manifests in terms of correlation functions. But like some concrete example that I know is that people study brain world models, and they can prove some restricted quantum focusing theorem. But it's more like still a GR like proof, not a field theory proof. Yeah.
Okay, if there are no more questions, let's thank Zihan again.
Yeah. Thank you very much.
Maybe some of us can stay and chat with Zihan a little bit, the faculty who want to. Yeah, maybe stop the recording.